Let's talk about the basics of an action potential within a neuron. So when we are looking at this graph here, a couple of important things to note. We see that the y-axis is labeled with the membrane potential measured in millivolts. So that's a measure of the difference in charge on the cytoplasmic side, so the inside of the neuron relative to the outside. And then on the x-axis, we have that labeled with time. Membrane potential starts at -70. That is the resting membrane potential of a neuron. So when a neuron is at rest, the cytoplasmic side of the membrane is more negative relative to the outside of the membrane. Now, if a sufficient stimulus is applied to get that membrane to threshold, which typically is measured around -55 to -50 millivolts, that is going to trigger the opening of voltage-gated sodium channels. When voltage-gated sodium channels open, that's going to cause those positive sodium ions to rush into the neuron because there's a higher concentration of sodium outside of the neuron than inside. So sodium is going to flood into the neuron, resulting in an increase in charge inside of the neuron. So this portion of the action potential is known as depolarization because of those voltage-gated sodium channels opening and sodium rushing in. Now at the peak of this graph here, we see at that positive 30 millivolt value, that is when the voltage-gated sodium channels are going to close, and it's going to trigger the opening of voltage-gated potassium channels. Now there's a higher concentration of potassium inside of the neuron relative to outside. So when voltage-gated potassium channels open, potassium ions are going to rapidly leave the neuron. That is going to cause the inside of the neuron's membrane to rapidly decrease in its charge. We call this portion of an action potential repolarization because the membrane charge inside is going to drop and return towards that resting membrane potential. Now, you'll notice that once we reach the terminal portion of this action potential curve, we see that the charge, the membrane potential, drops slightly below that of resting membrane potential. This period of time is called hyperpolarization. The reason for the hyperpolarization portion of the action potential curve is that the voltage-gated potassium channels, once that -70 resting membrane potential is reached, are not fast at closing. So essentially, there's a slight period of time when there's a little bit of extra potassium that is going to seep out, resulting in this slight period of time where the membrane potential is below or more negative than that -70. That is why we call it hyperpolarization. From there, there's going to be resetting. The rest of the voltage-gated potassium channels are going to close, and the voltage-gated sodium channels are going to reset so that we can reestablish the resting membrane potential, and it is ready for another action potential to occur.